We are in Module 3 of Digital Forensic Essentials. And in this module, we are going to look to understand a little bit more about hard disks and file systems. In this module, we are going to be looking at several items. We're going to be looking at, number one, understanding the different types of storage drives and their characteristics. We're going to be looking at the logical structure of a disk, the booting process of Windows, of Linux, and of the Mac operating system, and of the various systems, file systems of Windows, Linux, and Mac. And we're going to look at using a tool, a couple of tools, Autopsy and the Sleuth Kit. And in this module, this is a very important part of forensics, because if you don't understand the basics of how a disk functions and how a system boots, then you won't be able to find abnormalities in that process and to identify portions of that process that seem to be fallacious, inserted, or nonsensical even. So it's very important to understand what exactly is going on inside a disk and inside the boot process in multiple operating systems. So let's get started and learn that. What we're going to start with is the different types of disk drives and the characteristics of those disk drives. So first of all, when you're looking at a disk drive, what is it? It's a non-volatile, meaning that when you turn off the power, the data still exists on the drive. It's a non-volatile digital storage, digital meaning that all of anything that you'll ever find on a disk drive is ones and zeros. That's it, ones and zeros. So non-volatile digital storage device that records data magnetically. And it's on actually a metallic platter that has a coating of ferrous oxide on top of a very thin sheet of plastic-like material. And that ferrous oxide, which is basically iron, allows it to retain a magnetic field that has a small enough resolution to represent either a 1 or a 0. So the read-write performance of the hard drive is directly proportional to the RPM, the revolutions per minute of the drive platter. So if you look at this disk drive, this is a hard disk, and this is not a SSD, it's not a solid state disk, it's a rotating disk. And this disk is rotating around. There is a motor that makes this disk spin. The disk spins at the same speed, and then we have a read-write head that's at the end of this actuator arm that is run by this actuator. It's a stepping motor that only allows movement of this actuator arm to sectors of the disk. So it has to be tuned into the exact sectors of the disk. So the sectors are what we see going around, right? And then we have clusters, and then we have tracks. So it makes sure that this read-write head is positioned above the tracks of the disk so that it can read individual sectors, individual clusters, etc. So that's what we have. You can't see tracks. If you could see the disk patterning, you wouldn't be able to discern it with your eyes. They're extremely small. And also, the disk itself is called a platter. And that platter, there may be more than one. It could be 2 or 3 of them, depending on the disk. And there will be a read-write head and an actuator arm poised right above the bottom side of this disk, and then the top side and the bottom side of the next disk. So you might have multiple actuator arms that move back and forth among the platter as it spins at the RPM rate, jumping from track to track so it could read clusters and sectors on the disk. The disk itself, in order to run, needs power. So there's a power connector depending on the model and the type of disk that you have. And there possibly might be jumper pins that can change the disposition of the disk, where it's going to be, how it's going to be used, etc., depending on how old the disk is. And there's also going to be an interface connector. In this case, they're talking about a SCSI connector, which is a small computer system interface. That SCSI is pronounced SCSI. But there are many other types of interfaces for disks, and there are a plethora of technologies that go into making these disks faster, last longer, be able to preserve data, all those types of things, depending on the vendor and the technologies that they use. But those are some of the basics of a hard disk drive. Next, we look at a focus on the tracks. So the tracks are the concentric rings that we have around those platters on the disk drive. And the read-write head on the actuator can access those circular rings one position at a time using that stepping motor. It can only go in one place. So in other words, it's not like a record player where you can move the stylus wherever you want. It can only go to specific quantized locations on that disk platter. And so the tracks are numbered so that it can be identified, so that the data can be accurately accessed. And so the read-write is actually performed by rolling headers, is what it's called, from the inner to the outermost part of the disk. And so if you want to zoom in on it a little bit, you'll see that we have a 3-platter system here going in concentric circles around the disk. We have our tracks, and then this is broken up into sectors. One important area of understanding in terms of hardware is track numbering, understanding of how that works in a disk drive. One of the areas you want to keep in mind with this is that all computer hardware, for the most part, numbers beginning with 0. So it doesn't start at 1, it starts at 0. And you can see this over here in the numbering of the heads in the head stack assembly, head 0 all the way through 5. So we have 6 heads there. And you can see we have 3 platters, and we have tracks going around concentrically, divided into sectors. So the track on the outer edge is going to be 0, and then we count up as we move towards the center. And depending on the technology, on the disk drive that you're using, the size of it, and so on, you're going to have different numbers of tracks. And these read-write heads are going to be on the upper and lower surfaces of the platter, very tightly packed because of the smallness of the tracks. And they're going to move in and out to locate the beginning and end and work through files. And so, for instance, you may have a file that begins in this sector and reads all the way to this sector and then continues on the bottom or on another platter. Normally, they try to optimize it on a platter basis, but you never know. And when we talk about fragmentation, and we'll talk about that in just a little while, that's when that file gets spread into multiple locations rather than staying on a single track, causing those read-write heads to have to move around a lot more. All right, so the read-write heads, the head stack assembly arms move together in and out to physically locate the same track number. And so the track location is actually referred to by a cylinder number in some cases rather than a track number, which is a group of tracks that start at the same head position on the disk. So this is done to help optimize the disk. And we'll also find, if you were to get into some of the hardware of a hard disk drive, that there are a lot of physical and logical optimizations made because we've had this technology for quite a while. All right, so let's talk about drive sectors. What is a sector? A sector is a physical storage unit on the disk platter. Each sector holds data. It's fixed, a fixed size, maybe 512 bytes for hard drives, maybe 2048 for CD-ROMs and DVD-ROMs, and some of the latest hard disks are down to 4,096 kilobytes per sector. So it really depends on the disk, the technology, etc. So each sector is labeled, and that labeling is for factory track positioning. So we have data for the labeling so we can find exactly what track we're on, what sector we're on, etc. So the optimal method of storing disks is contiguous. So we go around a track, and if we have all the data stored in one stripe, so to speak, in one track, that is very nice, because then what will happen is the read-write head goes to that beginning of that track and reads to the end of that concentric ring, and then it's done. So like you might have a file size of 600 bytes, and it is in two 512 byte sectors that are allocated, and they're contiguous, one right next to the other. And that's the best and most efficient way to read files on a hard drive. So one area that a lot of people are surprised is how sectors are addressed. So we have cylinders, we have heads, and we have sectors, right? So CHS, cylinders, heads, sectors. Those are what determine the address of the individual sectors on the disk. So we need to, it's like a map. We want to know where every single sector on the entire disk is. So let's say that you format a drive. When you format it, that's when it's divided into tracks and sectors. And so you have a formatted disk. It might contain 50 tracks, each of which is divided into 10 sectors. The track and sector numbers are then used by the operating system and the disk drive so that you can find stored information. And what surprises some people is that this formatting has nothing to do whether there is data or not on the drive. So if there is data on the drive, let's say that this disk is full of information and you format it, all that does is remove the pointers to the data on the disk and present that disk as empty to the operating system. When in reality, as we'll see a little bit later, there is still, at the point of formatting, all of the data that was previously in the disk. We'll talk about that a little bit more as we get deeper into disk drives. So if we look at the hard disk drive, specifically at the 4096 byte or 4K sectors, the newer drives have these for advanced formats. And so this is called Generation 1. There's Generation 1 advanced format, which is 4K sector technology. It's made to more efficiently use the surface area of the media. How does it do this? Well, what it does is it takes all these little 512 byte sectors and merges them into a single 4096 byte sector for more efficient handling. And so that's what we see handling here. And a couple of other features that you'll see here is in between each of these 512 byte sectors, there's a gap, there's a sync stripe, and then there's the address mark. So we see that in between. And see all of that, look at that. That is space that is wasted. That's a wasted space. When you merge that all together into one 5K sector, you only have one gap and one sync and address mark. And so you're not wasting any space. So all of this can be used for data. Whereas in the previous methodology, no data could be stored here, no data could be stored in between any of these 512 byte sectors. So yeah, it is more efficient, and we can squeeze a lot more data onto a disk than we ever could before. Now, speaking of squeezing data onto a disk, let's talk about the density of data on a hard drive. So density is something that we see going up and up over time. And so it's something we need to talk about. Data is actually recorded onto a hard disk using what's called zoned bit recording or multiple zone recording. So that's how the data actually gets put onto the drive. And so what happens is the tracks are combined together into zones. Again, this is another efficiency measure that we use to make that drive, that disk, as efficient as possible. And those zones, it really depend on the distance from the center of the disk. And each zone is actually assigned a number of sectors per track. So the track density is the space between tracks on the disk, which is defined in the areal density as the number of bits per square inch on the platter, and the bit density is the bits per unit length of track. So when you are examining a disk at low level in a forensic investigation, knowing this information can be very helpful. So when you look at CHS, again, cylinder head sector data addressing and disk capacity calculation, it can sometimes be a little bit confusing for people. So we look at the CHS addressing method. We address each physical block of data on the disk. And what this is, how this works is we have the cylinder radius, so that's the distance from the center to the edge, the head, which is the platter side, and the sector, which is the angular position. We put those together. Those are part of the elements that we use to address a physical block on the disk. So let's look at the calculation. So let's say that you have a disk drive that has 16,384 cylinders, 80 heads, 63 sectors per track. And we're assuming, in this case, that each sector has 512 bytes. So what's the actual capacity of the disk? Well, here is the equation. A little calculus here. Actually, it's just addition and multiplication, stuff like that. And in this case, it's all multiplication. The total size of the disk equals the number of cylinders, where we have a 16,348, multiplied by the number of heads, which we have 80 heads, multiplied by the number of sectors, which we have 63 sectors per track, and multiply by 512 bytes per sector. One of the other things you have to do is you have to cancel out the units, and in the end you come up with 42,278,584,320 bytes, which is 42 gigabytes, right? So that's what we have with that disk. So what about performance? You may have a disk drive that has not 42 gigabytes, but you might have terabytes of storage on a drive, but you want to be able to get that image, that information out. I said the word image because I was thinking about having a large video file, and you want to be able to have that stream at a very high resolution or whatever, or you want to be able to transfer files from one location to another. You really need good disk performance. So what happens is of each of the files that we have on the drive, this is how data is stored on the disk in terms of files, different file types, etc. So if you have an application and it's running in RAM, and that application requests a file, the hard disk recovers the byte content of that file and sends that where? To CPU, one at a time for further processing. And then the CPU will send portions of that to RAM and video RAM, etc., for processing. So while that's happening, how fast is it happening, we might want to ask. And it's measured by these factors. Number one, the data rate. This is the number of bytes per second that the hard disk sends to the CPU, and also seek time. So you know how I told you about that sound? These read-write heads are moving from track to track, sector to sector, etc., gathering that data. Well, let's slow it down into slow motion and zoom in on it. And this is the read-write head. And when it goes to this track, locks in on it, and then it reads some data from this track. And then it moves over to this track, locks in on it, reads some data there. How long does it take to move from one place to another? That is seek time. The amount of time to send that first byte of the file to the CPU and request the file. So here we go. The first file, the application has requested a file. We've looked at the GUID partition table and we determined that the file is located, oh, it's coming up, here it comes, let's move over there. All right, we're reading the file, and now we go through and read the entire file. It gets loaded to the CPU, and then it's off reading another file, right? So whatever that took for it to move from where it was to where it's going, and for the CPU to get the data back that it was seeking, all of that is in seek time. And so we can see that the mechanical aspects of the disk drive play the majority factor in how fast that it can be. So for instance, if you have a drive that has an RPM of 5,400 versus a drive that is 10,000 rotations per minute. So you have one drive that's moving this fast, and the seek head moves to the location, and it takes time for it to read it. But if it's moving 10 times as fast, that seek time is a lot lower. So we have physical impediments to speed with a rotational drive. Enter solid state drives. If you look at this, you don't see any platters. You don't see any read-write heads. You don't see any sectors, and you don't see any tracks because it's all solid state, non-volatile NAND flash memory to store that information. It's faster than a hard drive because there are no moving parts. It's quieter than a hard drive. Any place where you require a little vibration, that's very nice. And the performance, though, can depend on many different things, specifically that data connection. So we have several things going on here. Number one, you see these little black modules here. They all have the number 1 on them. That's the core of this unit, which is the NAND flash memory. So it is where the data is actually stored, made up of floating gate transistors that retain the charge state without power. So once that transistor changes state, it stays in that state. And then you save the data that way. Those are called floating gate transistors. Then over here for number 2, this is the controller. This controller is like the CPU and all the other circuits that are needed to manage the flow of data in and out of this SSD. And it's a processor. It acts as a bridge between all that flash memory and the computer itself through this interface here. But we also have something else here. If you look at number 3, we have DRAM. And this is volatile memory. So number 1 over here with the NAND flash memory and these floating gate transistors is non-volatile, but this is just regular DRAM, and it's volatile, and it actually provides faster read-write performance and helps speed up this SSD. Number 4 down here, we have the actual host interface right there. That's part of the interface that we're using. And then we have the power port. And down here, this is this green. See this green with the circuitry that is surface mounted all over this green board. This green board is the PCB. PCB stands for printed circuit board, and that's the solid state drive printed circuit board. Now, when you're using a disk drive in general, there are many different interfaces that you can use. Now, back in the old days, back in the ancient times known as the 80s and the 90s, we had ATA, PATA, IDE, EIDE. And I tell you what, working with hard disks back then was a lot more difficult than it is now. You had to have them in specific orders. You had to, depending on the vendor and the type of drive, the type of disk, and the type of technology, you had to have your jumpers in the correct sequence, and you had to go into the operating system and allocate memory. And it was crazy back in those days using ATA, which is the Advanced Technology Attachment. It was advanced for the 80s, yes. And the American National Standards Institute, ANSI, name of the drive became IDE, the Integrated Drive Electronics. And this was a standard interface for a long time. But you see the width of those cables? They were very unwieldy to use. See that little notch right there? You had to have the cable in the right place, and so you'd end up with cables with twisted configurations, and then you'd have broken wires, and it was a big hassle. Let's just jump down over here to SCSI. SCSI, SCSI, pronounced SCSI, Small Computer System Interface. It's another ANSI standard interface based on a parallel bus architecture. And back in the time that ATA and EIDE and IDE were popular, these were used in regular microcomputer architectures, whereas SCSI was used in servers because you could have multiple disks and they were easier to address for software, etc. There are a lot of reasons for SCSI, even though the microcomputer architecture for PCs began beating SCSI in terms of speed fairly quickly. Well, next we had ATA and SATA. SATA is serial attached SCSI, and it's an advanced ATA that uses serial signaling instead of the parallel signaling, which seemed to be a lot better in the beginning, but we can get faster speeds with serial signaling using SATA. So for desktop computer systems and some intermediary server systems, you'll find a lot of SATA in those, or a lot of people will say SATA or SATA, patata. The next one we have is serial attached SCSI. So the growth and maturity and evolution of SCSI in server systems finally resulted in SAS, which is serial attached SCSI, successor to SCSI. And as you can see, SCSI cables, by the way, could be every bit as huge as a ATA PATA IDE cable, but SAS cables are nice and small like SATA cables, meaning that I can have very thin line blade servers and 1U servers and have multiple disks on that server that are high speed, and a lot of SAS drives are almost about the same size that you would have for a laptop drive, so that you can cram then into a server chassis. So those are some of the major interfaces that we've had over the years. Oh, I forgot to mention PCIe. PCIe is the Peripheral Component Interconnect Express, and we use this for SSDs, high-speed serial expansion cards, integrating directly into the motherboard. And you can see, I believe it's on this end, where we plug it into the motherboard, and then we power up components from that PCIe interconnect. Right on. All right, let's have a look at this second section, which is explaining the logical structure. So we've been looking at the physical structure of a hard disk. Now let's jump on into the logical structure. What is the logical structure of a disk? Well, it is the file systems the software uses. And so the software really doesn't care. If you're running Microsoft Word and you're about to save a file, it doesn't say, what sector and what track do you want to locate this file? No, the software doesn't care about it. All it cares is it has a file system on which to load the information. So that is what software uses to store data on the disk. So a hard disk logical structure really is going to affect the performance, consistency, expandability, and compatibility of that storage subsystem on a hard disk. We'll look about what that means. What do I mean that the logical structure is going to affect compatibility or consistency? We'll see in just a few moments here. So different operating systems, Mac, OS X, Linux, and Windows, and also I want to say that Windows Server, like Server 2022, Server 2019, have different file systems and various methods of arranging the data in those file systems and controlling access to the data in those file systems. This leads us to clusters. A cluster is the smallest logical, not physical, the smallest logical storage unit on the disk. So it's a set of sectors within the disk ranging from cluster number 2 to 32 or even more, depending on how you format the disk. And so the file system divides storage on the volume into discrete chunks of data so that you have efficient usage. You have better performance on these. And those chunks are called, that's right, clusters. And so where you have files that are allocated into clusters, that's called allocation. We're going to allocate these files to clusters. So clusters are also known as allocation units. So probably one of the longest used file systems out there was, I should say is, because you can still use it on certain systems, the file allocation table, or FAT, a file system. And we have clusters that are linked with files that keep tracks of data in the hard disk file allocation table. What did we say? This is called file allocation table. There it is right there, file allocation table. So what we're going to do is track where all the data is using that table. So it's like a little, not really, but it's like a spreadsheet that shows you where things are located. So it's a file allocation table. And when we look at other file systems, there are other ways of allocating storage on the disk. Like for instance, if you're dealing with NTFS, or you're dealing with exFAT or FAT32, or you're dealing with EXF3 versus EXF4, EXT3, EXT4, or HPFF. There are so many file systems out there. We'll talk about some of them as we get a little bit deeper into this section. One area that's very important to keep in mind is cluster size. Cluster size really affects the performance of the disk. And also, it can be changed. You can alter it if you want to optimize your disk performance. And when you format the disk, you'll have a choice of cluster size in many different disk formats. And so the size of the cluster really depends on the size of the partition of the disk and the type of file system that's installed. Is it FAT? Is it exFAT? Is it ext4? Is it NTFS? We'll look at these as we get a little bit deeper into the class. A large cluster size, which is greater than one sector. So if you have a large cluster size, it has these effects. Number one, it minimizes fragmentation problems. It increases the probability of unused space, which means that you may have a 1 terabyte drive, but you're only going to have some hundreds of gigabytes of usable space. Right? Also, it reduces the disk storage area in which information can be saved. So again, like I was saying, you're losing storage area, and reduces the unused area on the disk. All right? So there are consequences to cluster size. Very important to know that logical designation. The next thing we talk about is lost clusters. Lost clusters, where are they? Where do they go? What does it mean? And if you look at the disk, if you look in, let's zoom in on this, you see that we're doing a check disk. With a check disk, you can use this for very many different tasks. And one of those is to have a look at what is going on with that file system. And one of the items that you'll find potentially is the number of lost clusters. We see bad sectors, lost clusters. And so what is a lost cluster? So your operating system, what it's going to do is going to say, hey, these are all the clusters